Hey, IB Physics, it's Mr. Tima here. Here is 4.1 circular motion and gravitational motion. I'm going to be kind of quick today. Got some notes here, got a couple videos, and we'll be back in class and things like that. So you can make sure to ask questions about these. But circular motion, okay, here's your um, assessment statements, if you will. Okay, warning. Again, when you're talking about circular motions, we have to change from degrees to radians because we're talking about lengths on a circle now. We're not just talking about degrees. Remember, if you see something in degrees, you're in degree mode. If you're talking about lengths on a circle, you're in radians. Okay, so rotation and revolution. Rotation and revolution. Those are very similar words, but very different words. Rotation are objects turning around its own axes. So we say, as the Earth rotates on its axes. But a revolution is when a body is moving around another's axes. So we say one Earth year is one revolution around the sun. But the Earth is always rotating every 24 hours, but it has one revolution every 365 days. Okay, so what do you think? What do you think about this? What do you do on this thing? This is an old school kind of merry-go-round, is what we used to call these. Okay, I used to hang out here at the edge and almost get flung off. It is a rotation because the axis, it's like a planet. There's a center axis that it's rotating around. How about this guy right here? With this blue dot. Yes, that would be a revolution. Okay. All right. And then finally, what do you think about these guys? Well, they're actually both being present. I know it's probably a little hard to see, but let's pretend there's the center dot. We definitely have a revolution going around the blue one. The blue is having a revolution around the dot as well. But if you really looked at these carefully, there is some rotation. The actual balls themselves are rotating. I know it's a little hard to see. Okay, so there are two types of forces. There's centripetal force. Centripetal force is a center-seeking force. It pulls objects into the circle. Centripetal force is usually referred to as FC, can be of friction, gravity, and outside force. And the other one is a centrifugal force. Now, what's interesting is centrifugal force feels like a force, but actually centrifugal force isn't even a force. Okay, it's an outward seeking force. The effects of inertia in a rotating frame of reference feels like being pulled outward. You're really never being pulled outward. Okay, and we're going to talk about that here in a second. So, for example, with centripetal force, an object in motion will always stay in motion unless acted on by an outside force. So, this ball sitting on a plate, if we move that plate and turn it, that ball will continue out at a right angle and continue to move forward. The same thing would happen here at the bottom part, but if you notice there's a block or a wall or anything in its way and it's actually stopping it, but it looks like it feels, if you were that ball, you feel like you're being sucked outward, okay? But you're not, okay? Same thing happens in a car. When this car turns right, it feels like that person in the blue is being kind of being sucked over to the red guy. Okay, but that's not actually what's happening. Okay, what's happening here, it's going to go back here in a second. What's happening is as the car turns, the blue person stays in motion and actually comes together with the red person. That's why we have seat belts and things like that. So back to this example real quick. That centrifugal force, that centrifugal force is the feeling of getting like sucked up against a windshield when somebody turns the car, or that feeling like you're getting sucked back into your seat. That's not actually what's happening. What's happening is you are moving and then something else is changing object. So when you're sitting in a car and someone accelerates really fast, you feel like you're being sucked back into your seat. You're feeling that centrifugal force. That's not actually what's happening. What's happening is you aren't moving and now the car seat is moving because of the car. So you get that car seat is actually hitting you in the back, making you feel like you're being sucked back until the car gets moving and then you catch up to it and then that force dissipates. All right. Oh, snap. Well, again, if we have tension and you were in outer space and you were spinning a ball around yourself and that rope snapped, you will always leave at a right angle. It's very important. So here's our little picture of a diagram, the vectors in circular motion. What do you notice? Take a second there. Some of you might be saying, well, acceleration is always pointing towards the center of the circle and it's always the same. And you would be right. That velocity, which we call angular velocity, is moving at a right angle at all times. And it may change slightly due to the fact that it has a different direction at different parts of the circle. But for the most part, it also stays constant. Again, here is a nice vector written out way of looking at that. There's my mouse. I'll move this out of the way so you can see it. Okay, but there you go. You have a nice vector there. You'll need that for tension towards the center on a string. You have gravity or mass times gravity, and you have that tangential velocity. So here's how we kind of write this out. Uniform circular motion, angular speed or angular velocity is constant. Okay, velocity is changing because of direction only. Okay, so here's our angular velocity, our angular speed or velocity. Here's our tangential velocity. It changes. Like we could say this is negative, and this is positive because of its direction, but the value tends to be the same no matter where. This or whatever it has. So if it was 20 meters per second, we'd say it's 20 meters per second anywhere on there. Just it might be negative depending upon its direction. We're not going to really hone in on that in this course. Radius is the same. We assume the radius is the same. The force points towards the center of gravity. That's what that means. And then acceleration points inward as well, usually in the same direction as that inward seeking or centripetal force. The net force is in the direction of the acceleration. All right. So some of you may know what a record is. It's getting harder and harder to think about what records are. People don't really use records. But back in the day, that was called like an album. An album had 33 and a third RPMs, which meant that when something was recorded on a record, that point would turn around. It would make one revolution. To make one revolution would take a certain amount of time. A regular album would do it 33 and a third times in a minute. So when they laid out the songs on records, they had to make sure the speed, because you could speed up a record and sound really fast, you could slow it way down. A normal record would spin at 33 and a third revolutions per minute. So like if dot B was here, dot B would go around here 33 and a third times every 1 minute. Okay. A normal record, a big kind of record, ones that you can still buy today, those were called 45s, and those would go around 45. And a CD went all the way up to 600 times. Well, the faster it goes, the less popping or interference there would be. So they were smoother. These are kind of like the small records that maybe you've seen. They're like super, they have kind of a bigger hole in the middle. All right. But back to the merry-go-round, you got to think this whole line is moving around a record. So we experience a larger tangential velocity as we move outward from the center. Think of it as a merry-go-round. If you were a merry-go-round, that thing that I showed you earlier, if you stand directly in the center, you may spin in a circle. You may have a rotation, but it's barely like you're moving because you're kind of not covering much distance at all around the circle. As you move out, you feel that fake centrifugal force where it wants to throw you out. It wants to throw you out, okay, and try to stop you. But there you go. It's trying to throw you out. You get out here towards the end as kids, man, this was like the dead zone. Like this was the most dangerous part you could be because you jump on and this sucker would shoot you out as fast as you could. All right. So I know these got cut off a little bit, but basically these are your one-dimensional motion equations put into circular equations. So velocity is displacement over time. Well, what is displacement on a circle? Well, we talk about angular velocity, and its displacement is really how many degrees did it move over an amount of time. Well, what is how far on a circle do you move? Well, that's 2 pi r over big T, which is the period, how long it takes. Okay, how long it takes to make one revolution. So really, the velocity on a circle is angular velocity is 2 pi r over the period or the amount of time it took. acceleration is a change in velocity over time. Well, if we know that this is velocity, then acceleration on a circle is just the angular velocity final minus the angular velocity initial divided by the time. And then finally, we have force equals mass times acceleration. Okay, mass times acceleration, which we know. But what is acceleration? Acceleration is velocity squared over the radius, which we're getting to. But so we substitute that in. So those are important equations for you to use. Okay, well, how do we get to F equals M, or how do we get acceleration on here? Well, it's just Newton's second law, F equals ma. Okay, but mass, okay, mass, we're not at mass yet, sorry, I apologize. Acceleration is this breakdown, the ability of taking our velocity, okay, and divide it by the radius. So really acceleration is v squared over r. And then we finally get to our new force equation. Centripetal force is mv squared, I know that got moved, v squared over r. Okay, so you that are very good at math, you can see this, but basically what you need to understand is Newton's second law is F ma, but on a circle, it's F equals mv squared over r. Again, I have these on here as normal. Since they are vector quantities, they move as vectors, they leave at right angles, and since they leave at right angles, we can then calculate them so. I know that's really blurry for some reason, but Fc equals mv squared over r, and centripetal acceleration is just v squared over r. All right, so what do we know? All right, what do we know when we come down this hill? Well, when we go down this hill, we know something. What do we know? When something starts up here, what do we know? We know it's potential energy. You're absolutely right. So if we know it's potential energy here, then we know what down here? Yeah, we know it's kinetic energy. And if we know our potential and kinetic energy, then we probably know it's mechanical energy. Yeah, we probably know it's mechanical energy. All right. So if we know it's kinetic energy down here, we then know we could probably, if given different things, depending upon what we have, we can find its velocity. We could find its mass. We probably know its mass already. Okay. We know that when it's down here, we have any kind of Suvat type thing going on, because basically once we know the energy down here and we find its velocity, we know any kind of Suvat type stuff down here, because now we just have simple one-dimensional motion. Once it comes down the hill, this is a flat track. And then once we get into this circle, now we start worrying about our angular acceleration, which was on the last one, which angular acceleration is v squared over r. Okay, it might ask you, what is its centripetal force? Well, its centripetal force, again, is m v squared over r. Okay, and we get that because we're now in the circle part. So even though this is all related, basically we have an inclined plane part, we have a Suvat part, we have a circular motion part, and we have another Suvat part over here. They're all related to each other. Okay, even though that's one big complex problem, you have to take each part individually. All right, so let's just look at this little problem right here. It says an F-14 traveling at 500 meters per second pulls out of a dive, moving at an arc radius of that. Okay, what is the plane's acceleration? Well, first of all, we have to think about what is acceleration in a circle. Acceleration is v squared over r. So it's a pretty simple problem. You just take 500, square it, divided by 4 times 10 to the 3, or 4,000, right? And you should get that right there. You should get that right there. Again, I always put this up here, but it says every summer vacation needs a little recess now and then. He's like a super nerd. So, you know, this is an inclined plane. Okay, this is tension. This is what we just talked about. Okay, this is basically torque, if you will, and then this is gravitational, which we haven't gotten to. But you know, he's a super nerd, so he likes to think of all the equations. All right. So finishing up, getting towards the end here. A bicycle on a track, or think about somebody running on track. If you didn't know, a high school track is slightly slanted inward. Okay. It's actually higher on the outside and lower in the middle. And that is out of design because anytime you're on this, remember, because of your weight, because of gravity, because of this idea of an inclined plane, we know that it's pulling and centripetal forces pulling you towards the inward of a circle. If you've ever watched somebody run a really fast race, when they wreck or if they slip or if they fall inward towards the track. Okay, you can see this in NASCAR. When there's wrecks, they wreck into the infield usually. Okay, if you're running a race, if you've ever been to a track meet, and you see them run the 2 mile, and those people like get so tired they almost collapse at the end. They collapse inward towards the track. They very rarely go out to the fence. They go inward towards the track, and that's normal. So there's this thing called the wall of death. Okay, the wall of death of motorbikes traveling around the inside of a cylinder on vertical walls. So what they have to do is their tangential velocity has to be so great that it overcomes the pull of gravity downward. Okay, which is kind of crazy to think about, but I already have it pulled up on here. Of course, I have this. That you don't see this very much in the United States. Okay, sorry about that, wrong thing. You don't see that very much in the United States. You see this in foreign countries. So we have our motorcycles, which are very easy. I'll turn down the sound so you can hear me a little bit. But what you're going to have here is these cars down here. Now notice the cars can't just drive straight up onto this. They would never get out of there, right? It's kind of like if you're ever stuck in a pit, you should never try to run straight up a wall. You should try to run in a circle and build up speed to get out of there. Here we go. So you got to think, by the perception of the people on the motorcycles, it looks like they're just driving straight. To them, they don't look like they're on the side because it's all about a feeling of a relative motion, if you will. So check out this car. He's got to speed up. He's got to go. He's got to floor that sucker. Okay. And if they would ever stop, then gravity would overtake. Okay. And they would fall straight down. You're going to see a guy try to stick his body outside the door here. Okay. But again, it's pretty ridiculous actually. But yeah, they have to gun those cars because they have their tangential velocity has to be greater than the acceleration due to gravity. So their acceleration has to be greater than gravity to stay like this. Either way, a little dangerous. Again, not the safest thing, but kind of cool to look at. All right, and then finally, we're going to look at. I'm sorry about that. I want to make sure I don't miss anything. Oh, here's our picture. So again, that tangential velocity, we got to be faster than that downward force. And then finally, I like this guy. It's an older video, but he does some experiments that I can't do because we're not in school. So we would do the one with the bucket and stuff, but we can't do that. So here we go.
Circular motion. All right. To go in a circle, you have to be pulled towards the middle of that circle, right? So if you ride a merry-go-round, you're going around on a merry-go-round, you feel like you're going to be flying off to the side, right? That's because you're being pulled to the middle of the circle. So if I want to spin this in a circle, I have to pull it towards me because I'm the center of the circle. All right, and that's circular motion. We call that pulling towards the center centripetal force. Okay, and so you can do real cool tricks with that. As you can see, I'm going to take this little platform here and put some water on it and make it go in a circle. Got it on the table here, and now I have to pull it towards the center of the circle, and it will go in a circle. All right, so here we go. 360 degrees, upside down, amazing cup of green water. Now, why did this work? So when this was traveling in a circle, remember, it was being pulled towards my finger. Well, really only the platform was being pulled towards my hand, okay? And so what was causing this to go towards my hand? Well, the platform was pushing on the cup, Okay, so I pulled on the platform pushed on the cup, so the cup felt like the platform was pushing up on it. Just like when I'm standing here on the earth, I feel like the earth is pushing up on me, supporting me, because really gravity, the ground is pushing up on me because gravity is pulling me down. So I feel like I'm just standing here. So this thing sort of had artificial gravity went around in a circle. So now let's see what happens when we use this idea of centripetal force in a couple cool examples. So now we're going to do a demonstration that's pretty hard to do visually for you, but we're going to try it anyway because it's really cool. I have a lit candle right here, as long as I don't burn my finger. All right, and I'm going to spin it in a circle. And we all know that the flame of a candle goes upwards because hot air kind of rises. Well, what we're going to do is we're going to kind of artificial gravity here because we're going to spin this around, remember, and we're going to spin it in a circle, and it's going to go around fast in a circle. All right, and so what happens is it's going to think that that way is up, towards the middle is up. So if I put this on, this is to keep the candle from blowing out, and spin this really fast. Watch where the flame of the candle points. It's pointing just a little bit towards the middle. Let me try one more time. A little hard to see. Here we go. It points towards the middle of the circle because basically what's going on, again, is that all the air inside this bell jar is being pushed on by the bell jar, okay, pushed that way. And so the air kind of flows down this way, and it's as if you have artificial gravity pulling you this way. You're being accelerated that way, just like the earth is accelerating you. And so the flame will point towards the middle. Now we can do the last cool thing. It's time for the finale, the paper saw. What I have here is a saw made of just normal everyday paper. All right, you've gotten paper cuts before. Well, we're going to take this paper and use it to cut a piece of wood. That's lightweight wood, but it's still wood. Now, how are we going to do that? Well, if we spin it really fast, remember, it's being pulled towards the middle in order for it to go in a circle. So what happens is this piece of paper is going to become very taut, right? It's trying to fly out in all directions, but it's being pulled in, and so it's going to be very tight, and it's going to get really stiff. We can actually cut a piece of wood with a paper saw. There we go. And we have the paper saw cut right there. All right. So until next time, watch out for paper cuts.
So he's a little dorky, just like me. But I think the paper saw is really cool because you got to think about it. The faster you rotate it, those particles are being pulled inward, which kind of makes that counter action of being taught that a piece of paper could literally cut wood and things like that. So I hope you enjoyed this. Again, I know they were a little long, but we'll see you next time. And